presentation, and at the end we're gonna have time for Q&A. So we all need to
All right, sounds good. Ready to start? All right. Good morning, everybody. My name is Susan Yang, and I am the project manager of WaterWise Engineers. Today, we will be discussing our project scope for improving stormwater storage and water quality at the Lyle Center using green stormwater infrastructure. Before we present, we would like to thank our faculty advisors, Dr. Majid Sadeghi and Dr. Ali Sharbat, for providing their industry knowledge and their support for our hydrology team, environmental team, and our outreach team. Our agenda for today will discuss green stormwater infrastructure and its benefits, provide an overview of our project scope, and evaluate how our project meets our project goals and benefits our campus. So what is green stormwater infrastructure? Green stormwater infrastructure, or GSI, are nature-based solutions that utilize native plants and drainage systems in order to mitigate environmental issues and provide functional aesthetics for the public. They utilize low-impact development, or LIDs, which mimic the natural hydrologic processes that manage runoff and water quality. Some aspects of the hydrologic cycle that we acknowledge when optimizing our GSI are precipitation, infiltration, and evaporation. It is best to understand how water behaves in our atmosphere and how it enters and leaves our earth to understand how to utilize these natural solutions for our technology. In urban settings, they often use concrete or asphalt for infrastructure such as roads, rooftops, or parking structures. They create impervious cover, which accumulates more runoff over time and allows pollutants to travel more freely. Thus, in these urban environments, flooding and poor water quality are often present. Climate change may also disrupt parts of water cycles, such as precipitation. In our region of Southern California, because of inconsistent rainfall, we experience extreme weather events such as flooding or droughts occasionally, and these can cause impacts with local water supplies, as well as causing conflicts with maintaining existing infrastructure. Some benefits that GSI provides with native plants: it can slow down the speed of runoff and allow it to infiltrate into engineered mediums. This can ensure that any local community can recapture and reuse water that is free of any pollutants in these urban environments. Now to give an overview of our project scope. Our project resides in the city of Pomona, which borders the eastern side of Los Angeles County in the state of California. The main campus of Cal Poly Pomona is approximately 1,500 acres between Kellogg Drive, University Drive, and Temple Avenue. Our project at the Lyle Center is southwest of the main campus on a 16-acre lot between West Temple Avenue and South University Drive. Our team prioritizes our scope on the eastern side of the Lyle Center in order to accommodate for any ongoing construction to existing facilities, as well as to avoid any conflicts with the Lyle Center's master plan. The Lyle Center is an educational facility facilitated by the College of Environmental Design, managed by Associate Dean and Professor Andrew Wilcox. Their curriculum majorly focuses on cultural studies, natural processes, and technology to create sustainable solutions to mitigate any climate issues or environmental issues. Their involvement with the main campus of Cal Poly Pomona is how they provide fresh produce for the farm store, as well as aiding student programs such as Poly Pantry, which helps alleviate food insecurity for students. They also promote campus events such as Farm to Pantry, which also support these campus programs and encourage community engagement between students and faculty members. Our team consulted with Andrew Wilcox and conducted several site investigations to address any issues that our scope would like to resolve. We identified areas where existing facilities and existing areas require some maintenance, and other areas of accessibility that could be improved for any future visitors, students, and faculty. There are several undeveloped areas behind existing vineyards and educational facilities that would benefit from the presence of GSI to garner that attention and increase the amount of visitors that visit this facility. Andrew also displayed interest in having our team implement solar panels into our scope to encourage renewable energy generation for the Lyle Center and our parking lot. We chose the Lyle Center because it meets the criteria to showcase GSI, as well as to spread awareness and education of how it benefits our community and the environmental benefits as well. We conducted a survey of with 109 students and faculty members to inquire their familiarity with GSI and its benefits. And our results show that approximately half of our sample size is unfamiliar. And although GSI is not a new innovative technology, as shown in an example of a GSI that actually exists on the campus, we aim to connect engineering solutions and environmental studies that the Lyle Center provides in order to expand on those solutions and spread awareness. To do so, based off of our demographic and the issues that we addressed as of earlier, we formulated our project goals to improve stormwater quality through LIDs, creating educational opportunities about GSI for students and other visitors, supporting Cal Poly Pomona's climate and sustainability goals, as well as maximizing green space and accessibility for future visitors. Thus, to do so, our scope will involve a newly constructed parking lot, followed by a green space with an amphitheater, followed by a rain garden. We will also implement a swale and a cistern that will collect all of our runoff free of pollutants and other contaminants. But to do so and to optimize our design, we had to acknowledge any preliminary site analyses and other limitations to ensure that our designs are safe and meet industry standards. I will pass off our first segment of preliminary site analysis to Isaac.
Thank you, Susan. Hello, I'm Isaac Kim, the geotechnical specialist for this project. Our site is located near the San Jose fault line, indicated by the red line that crosses through the CPP campus. This is a risk factor we have to consider due to its close proximity of 0.5 miles and because of its earthquake frequency. In tandem with these earthquakes is the liquefaction zone indicated by this blue area. This means that the soil on our site has the potential to act like a liquid during earthquakes, which can destabilize our site and increase the potential of a landslide. We conducted a soil survey of the Lyle Center and discovered that our soil was primarily a type C soil. These soils are categorized by their granular shape and are generally considered unstable. And beneath these granular soils is an expansive clay. If exposed to water, will swell up and undergo volumetric changes. Some of the challenges we had associated with that was having no infiltration during construction, as if we want to protect the expansive clay from any outside influences, as if it can destabilize and cause damage, which will not only impact our GSI development, but also any other future Lyle Center projects. Some other challenges we had was having the high groundwater table, as the groundwater can potentially leak into our expansive clay, and the previously mentioned landslide potential, but also having a steep slope and the congestion of roads. Next, I will hand it off to Kimberly.
My name is Kimberly Estabio, and I'm the water quality technician, and I will be presenting the existing contaminants and the impacts. During our site inspections, we have identified several contaminants. These include trash, oil, and industrial chemicals such as pesticides, paints, and solvents. We also found heavy metals as well as excess sedimentation, which can obstruct the drainage and reduce infiltration. Given that the construction is still ongoing, we are seeing continuous exposure to several contaminants. Exposure to industrial chemicals and heavy metals can lead to serious health problems such as respiratory issues and skin irritation. Water pollution is a major concern. As runoff flows over the site, it can carry oil, grease, and industrial chemicals into the waterways. This degrades water quality and poses risk to both the ecosystem and the communities. Lastly, we see ecosystem stress from soil contamination and poor drainage. Soil contamination can affect the plant health, and poor drainage can lead to erosion. Now I'm going to pass it on to Colton.
Thank you, Kimberly. Hi, my name is Colton Pietzola, and I am the hydrology lead. Now we will talk about the preliminary site analysis for our watershed. Oh, sorry. Apologies. So over the course of the year, we made multiple site visits to our project location. And this is in order to better find out information about the elevations, terrain, the important landmarks, as well as general flow lines for our runoff in the area. And from these project site visits, we were able to compile pictures and notes and combine those using Google Earth Pro elevation profiles to plot out high points for our watershed area or in our general project site. Additionally, we produced a grid overlay over the top of our site area in order to better serve as a contour line map to more accurately determine these high points, as well as figure out the general flow paths in our watershed area, as well as the final outlet points over here in a pre-existing storm drain. So we were able to produce this blue area, which will be our watershed area, which we will reference off of for the rest of our project. It is composed of roughly 6.5 acres, and this will be our reference point for all developments later on that we'll talk about. So for our project design, we need to capture the first flush. The first flush phenomenon is where during the first hour or two of a storm event, we find a sharp increase or large amounts of contaminants found within the runoff compared to later parts of a storm event. And this is caused because of a buildup of contaminants because of dry periods, droughts, and a lack of consistent rainfall periods, especially which plague Southern California as a whole. And the Los Angeles Municipal Stormwater Permit requires capture of this first flush in the form of the 24-hour 85th percentile runoff amount. So for our design, for our GSI, we need to capture at least this 85th percentile amount. I say at least because we first have to make a determination between capturing what's greater between a base amount of 0.75 inches of rainfall depth versus the 24-hour 85th percentile amounts, which we found using the Los Angeles County hydrology map for our project site to be roughly 1 inch. So since 1 inch is greater than 0.75 inches, we will design for that. Additionally, our GSI is designed to convey a 25-year storm 24-hour period event for a depth of 5.72 inches. So to reiterate, we will be capturing runoff of depth of 1 inch, but we will be conveying 5.72 inches in the form of a 25-year storm event. And here is a table of our watershed analysis. So basically this compiles all of our data for the flow rates as well as the capture volumes for the parking lot, green space, rain garden, and swale, respectively for the 85th percentile amounts and the 25-year storm event for a 24-hour rainfall duration. Now we will talk about our first project development, the parking lot. The main purpose of our parking lot is to collect and direct rainwater runoff within its impervious area to later downstream GSI features. It's located northeast of the Lyle Center entrance in an undeveloped uphill area. That area will also replace the existing inactive solar panel structures. There will be an open air parking lot, meaning that it will not feature a structure or any sort of overhead clearance, which makes the design simpler. As far as accessibility, there will be 3 pedestrian entrances located here, here, and here, which allow accessibility for foot traffic, as well as 2 bike lane connections located at 2 of these pedestrian entrances, which allow for students, faculty, and other visitors to the Lyle Center, as well as to our amenities provided in our green space to use bicycles. So as far as connections, the parking lot's pedestrian pathways will connect to our green space area just to the south of it, and the runoff will be drained via a drainage ditch on the southern portion of our watershed to the right that drains directly to our rain garden area located here. So some features of our parking lot: it'll feature 108 total parking spaces, 5 of which are ADA compliant. These 5 ADA stalls meet all parking requirements for the California ADA parking requirements as far as spacing and safety features. Additionally, our parking lot will have 2 solar canopies that will encompass the double stacked parking aisle area in the middle here, or one located right here and one located right here. Attached to the concrete supporting pillars for these solar canopies will be lights that will provide visibility and safety during nighttime and for students who are concerned about that. Also, it will feature bike racks located at each of the bicycle entrances, access points, and a bicycle service station for those students who want to service their bikes. So our parking lot is composed of roughly 43,000 square feet of impervious concrete at a 2% slope gradient. This 2% slope gradient still falls within ADA standards and compliance, and the total energy for solar canopies in the middle here, the production will be roughly 100 kilowatt hours. So that'll suffice for all parking lot power draws, as well as provide the Lyle Center with an additional alternative renewable energy source. Now I will pass it off to Ryan to talk about the rain garden.
Thank you, Colton. My name is Ryan Huang, and I'm part of the environmental team as the LID specialist, and now I'll be going over the rain garden implementation. So starting off with what a rain garden is a type of LID system that consists of native plants, shrubs, and flowers that collect water from surrounding impervious areas, which helps reduce runoff as well as improve water quality. As for how a rain garden works, native plants and coverages will separate existing contaminants as it's filtered through an engineered media that consists of engineered soil and wash gravel into an intricate pipe system where the treated runoff will be collected. As mentioned before, this does help with water quality as well as groundwater recharge. Additionally, rain gardens do play a big role in supporting local biodiversity as well as reducing erosion and flooding risk, making it an eco-friendly solution for urban stormwater management. So moving on to our scope, we believe a rain garden would be very beneficial to the Lyle Center as we placed it in a location where it could capture and treat a lot of runoff from the site. However, other than its practical use, a rain garden does add a standard of beauty to our campus, as the native plants are capable of attracting many different wildlife species, such as butterflies, bees, and birds, creating a natural habitat right on our campus. As for the plants that we went with, as shown on the screen, the California buckwheat, golden yarrow, and seaside daisy are excellent choices, as they are all native plants that are drought resistant, able to survive fluctuating moisture levels, as well as not needing much maintenance once established. Other than the aesthetic values these plants provide, they do help with pollutant removal. Their roots can help prevent soil compaction while uptaking nutrients and filtering contaminants from the road. Next, I'll pass it off to Chris, who will discuss the rain garden.
Thanks, Ryan. I'm Christopher Landon. I am the CAD technician on the hydrology and design team. We ultimately decided on a spot that's just north of our vineyard and to the east of our green space. We thought this location was ideal because it's downstream from the amphitheater and the green space, and we would be able to easily pipe water from our parking lot to our rain garden through gravity. The square footage of our rain garden is just under 2,000 square feet, and that is greater than the 4% required of the area of our watershed, which is shown in this picture right here. We derived all of our methods and calculations from the City of Los Angeles Low Impact Development Best Management Practices Handbook. We designed the flow in a sheet flow over the riprap rocks and the vegetation, and it is planted in 3 inches of mulch, under which is a engineered soil, which is composed of compost, topsoil, and sand, designed to promote plant growth and water filtration. Underneath is a wash gravel layer of 1-inch diameter gravel, enclosed in which is a perforated pipe to collect the water after it is treated and send it to our cistern. Our entire rain garden is enclosed in an impervious liner and a concrete planter box to withhold the water and to prevent infiltration into the surrounding soil. Next, I will hand it off to Alex to talk about the design of our swale.
Thank you, Chris. Hello, my name is Alexander Lam. I am the hydrology specialist for this senior project. I'll talk about the swale. So first of all, what is a swale? A swale is a ditch in which green plants are planted in order to help convey water downstream, as well as treat any pollutants that go through the plants. So for our case, we decided on Berkeley sage due to its low maintenance, its drought resistance, and its also flood tolerance to flood conditions. Next up, here's the plan view for our swale. We plan to have the swale placed on the south side of South University Drive. This is so that water flowing from South University Drive will flow through our 2 NDS channels that will help convey it to the south side and into our swale. Our swale is 200 feet long and around 11.25 feet wide. This will help collect as much water as needed as for the first flush. Here is a plan view for our swale. The water flows above or around the riprap onto the bed of our swale, onto 6 inches of engineered soil and 4 inches of gravel, which flow into a French drain on the bottom, which flows to our cistern. Speaking of the cistern, we plan to place it here next to South Campus Drive in order for good accessibility to clean out the sediment traps that are included with it. For the design criteria for our cistern, we need 1 inflow, 1 outflow, and 3 sediment traps as is NDS standard. we plan to capture 6,200 cubic feet of water, which includes our first flush phenomena and the 1-inch 85th percentile. The cistern itself consists of 42 pieces of 41-inch high NDS storm chamber units with 3 start units, 36 middle units, and 3 end units. There will also be an impervious liner underneath to stop infiltration. Here is a plan view of our cistern. The cistern itself is organized into 3 rows, where the water will flow in from the inflow, fill up the first row, and after that fills, the connecting pipe will flow into the second one, and finally the third one to the outflow. There will also be an overflow pipe, so volumes of water over the 85th percentile will flow into the storm drain. Next, I'll hand it off to Chris for the green space.
Thank you, Alex. Hey everyone, my name is Christopher Cal, the Outreach Team Lead and Website Designer, and I'll be discussing green spaces and what they mean for our project. So green spaces are urban spaces usually covered in grass, shrubs, and trees, and other types of vegetation. They're important for urban landscapes where we often don't have access to spaces outdoors, and they're vital for communities and to be healthy. Our green space includes 32,000 square feet of coverage, mixed-use pathways, picnic tables, study spaces, and multi-use paths. Our green space also features only native drought-tolerant plants and contributes water directly to our rainwater. Furthermore, our green space features thoughtful amenities such as rugged outdoor hammocks, ADA accessible picnic tables, park benches, trash bins, and hammocks, all of which are made out of recycled plastics and contribute to our sustainability goals. Now to you, Jess.
Thank you, Chris. Hi everyone, my name is Jessica Wang and I am one of the outreach representatives. One of the key features we're excited to propose for the site is an amphitheater. This is to draw in more visitors, foster engagement, as well as bring the CPP community together to host their own events. Whether it's freshman orientation, musicals, or outdoor lectures, this place creates a versatile venue. The amphitheater will have concrete terrace seating, which can seat up to 400 people, as well as a main stage that is 328 square feet. Additionally, it is located in between our green space area and our rain garden area and encompasses nearly 6,000 square feet. Beyond a performance venue, this area serves as a community hub where campus goers can feel a deeper sense of connection and a deeper sense of ownership with Cal Poly Pomona. And now I will pass it off to Alyssa.
Thanks, Jess. Hi, my name is Alyssa Vrana. I am an outreach representative, and I will be discussing our educational plaques that are located throughout our project site. Each plaque has a QR code on them for visitors to scan to learn more information by being directed to our website. You can feel free to scan the code down on the screen. You also have another opportunity at the end of our presentation. There's 4 different types of plaques. This plaque here is defining green stormwater infrastructure and laying out its benefits. The plaque on the left is dedicated to our project itself and describing our engineering aspects. There will also be plaques that will give information about the native plants we chose to place in our green space and throughout our project, as well as plaques dedicated to certain aspects of our engineered GSI projects on our site. Now I will pass it off to Diana to discuss her review.
Thank you, Alyssa. Hello everyone, my name is Diana Maniakov and I am the environmental team lead. With our site located on school grounds, all construction and design projects must comply with the California State University permitting requirements. Therefore, a CSU building permit must be obtained before any construction, demolition, or any site improvements begin. Here we have some key permits required for our site. We have the United States Environmental Protection Agency. This protects the human health and the environment. Then we have the National Pollutant Discharge Elimination System under the California State Water Resource Control Board. This is for stormwater management during the construction phase. Next, we have the ADA compliance and the grading permit under the Los Angeles County Department of Public Works. For the ADA compliance, this ensures that the Parking area, green space, pathways are accessible to all individuals, and for the grading permit, this is required for any excavation or earthwork activities. Lastly, we have the Rule 403 dust control under the Air Quality Management District. This is mandated to minimize dust pollution during the construction phase. With these permits, it helps ensure the project complies with safety, accessibility, environmental, and operation standards. Now I'll hand it off to Ingrid to talk about Envision.
Thank you very much. Good morning, everybody. My name is Ingrid Camacho. I am the Envision Specialist. And I'll explain what Envision is. Envision is the framework that we use to assess the sustainability and resiliency of our project. Envision is a comprehensive rating system that helps project teams make better decisions or informed decisions towards more sustainable and resilient projects. It consists of 64 credits that assist us in project planning and project design and delivery. In order to evaluate our project, we use Envision's pre-assessment checklist, which includes 5 categories, including quality of life, leadership, resource allocation, natural world, and climate and resilience. Based on the current project phase, we received a score of silver. This means that we achieved at least 30% of the applicable points. This is a good starting point for a project, which signifies that our project team is committed to sustainable and resilient solutions. Now I'll pass it over to Miriam for cost estimate.
Thank you, Ingrid. Good morning, everyone. My name is Miriam Colazzo, and I'm the Assistant Project Manager as well as the Dedicated Cost Estimator. Today I'll be going over our total project cost, some potential funding sources, as well as some key design elements we use throughout our site. Now to start, here is a high-level overview of our total project cost, which was estimated at $5.8 million excluding contingency. Now our total construction cost was estimated at $4.9 million. A large share of this was due to our parking lot, shown here, as we chose to implement not only the solar panel canopies, but also the need for earthwork to be done in that area prior to construction. Next, we have our operation and maintenance costs for the very first year at $54,000. This allows us to not only monitor, but as well as maintain all of our BMPs and LIDs introduced through the site. Next, we have our permitting costs at $97,000. This was taken from 2% of our total construction costs, which is an industry standard. And finally, we applied a 30% contingency cost in order to mitigate any risks or challenges that we may face, such as any permitting or material delays, design changes, or site and infrastructure issues. Throughout our design process, we prioritize sustainability as well as resilience. We did so by implementing the following elements. We have our green infrastructure, including native and drought-tolerant plants, our impervious liners, our riprap, and our layered soil mix. Next, we have our stormwater system, comprised of NDS storm chambers, which make up our cistern, perforated PVC pipe, and an eco-drip irrigation system. And finally, for student amenities as well as energy infrastructure, we implemented the aforementioned solar canopies over our parking lot. We have porous concrete bike lanes, as well as the picnic tables, benches, and hammocks made from recyclable materials, all for our students to use. And finally, for our proposed funding strategy, we assumed 100% grant coverage, as this was the best case scenario for our project feasibility. Now, the largest contributions are going to come from the CSU system, as well as the Safe Clean Water program, coming in at 30%, because our project not only directly benefits campus infrastructure, but it also improves stormwater quality. Next, we have DWR's Proposition 1 grant program and the US EPA. These agencies are going to fund 10% each, as our project directly aligns with their individual goals for sustainability, outreach, and reuse. And finally, we have our smaller contributions coming from Los Angeles County and the California Water Board, as they will mainly assist us in permitting, compliance, and any other regulatory needs. I will now pass it back to our project manager, Susan, to conclude our presentation.
Thank you, Miriam. To drive our point home, all 3 of our teams have conducted thorough research from hydraulic analysis, environmental analysis, and community engagement to ensure that all 5 of our scopes completed or met our 4 project goals and met industry standards. The focal point of our project scope is to ensure that these engineering solutions strive for a greener future and encourage community engagement, as well as spreading awareness to these communities for our local community and our institution, because after all, sustainable practices start with us. Thank you. Now the floor is open for questions, or we also have a poster that summarizes